Welcome to the show. If you were not expecting this call, thank you. Goodbye.
A launching pad to say, I can do this.
Hey, Dr. Banerjee.
Guy.
I had a quick question about one of the homework problems, if you're free for a second.
Yeah, just a second. So my Zoom went down. You guys can see the screen, I hope, right? Yeah, go ahead with the question.
So
what
on
was the
number
question?
3.17, the first part asks to calculate the hole concentration, and we're given the electron concentration and NC and NV. So are we supposed to express that in terms of a temperature dependence? Because you can calculate Ni using just NC, NV, and this electron gap, or the.
So whenever I don't specify temperature, you can assume it's room temperature, which is 300 Kelvin.
Oh, okay, cool. And then the last problem on the homework is about the Hall effect. So we should just work on that one after class today.
Sure. Last time I told you that you could hopefully read ahead, but I'm going to cover this first thing in the morning. Yeah, you can do it after class. That's fine.
All right, thanks.
Oh, I was in the wrong meeting apparently. Oh, Professor?
Yes.
For office hours, do we just call you on your cell phone?
Yeah.
Okay, because I wasn't sure if we were supposed to like just in the Zoom call or if we were just supposed to call that number.
Yeah, just call me. Yeah.
Okay.
All right, let's get started. I'm going to quickly wrap up chapter 3 and then start off on chapter 4. For the midterms, however, you'll only be responsible for chapters 1, 2, and 3. All right, so last time we stopped at the discussion of the Hall effect, which is a very standard technique for measuring carrier concentrations in a semiconductor, along with the resistance measurements, which can be used to also calculate the mobility, okay? So the way that works is you take a rectangular bar of the semiconductor, like a resistor, and we know that we can apply a voltage across that, say in the X direction. And then if you flow a current Ix, you know that the resistance of the bar equals V along the X direction divided by the current flowing in the X direction, okay? Now, of course, we can write down the formula of a rectangular resistor as rho, the resistivity, the length of the resistor divided by the cross-sectional area. In this case, that is the width W times the thickness T, okay? So I write the cross-sectional area as the width, the thickness times W, all right? The resistivity, rho, is given by the 1 over the conductivity sigma, and we derived last time, is given by this expression where you have contributions due to electrons and holes times the corresponding mobilities times the electron charge. Now, although this is the most general expression, in practice, depending on whether it's P or N type, one of the terms will dominate. So in this case, assuming it's a P-type semiconductor, the minority carrier electron part will be negligible. Okay, so the resistivity becomes 1 over Q mu P times P. Let's assume it's a P-type semiconductor. All right. Now, going back to this expression for the resistance, rho L over the cross-sectional area, you can break it up as a product of two terms. The first term is given by the resistivity divided by the thickness of the resistor times L over W. Now, this quantity, rho over T, is known as a sheet resistance and has units of ohms per square, while the quantity L over W clearly is a dimensionless quantity because length has units of dimensions and so does W. So this quantity L over W is known as the number of squares. What does that mean? What it means is, looking at this resistor from face D to C, you can break down the value of the resistance as an parameter rho RS, the so-called sheet resistance, which depends on the material parameters, rho, and the thickness of the film, while the second term, L over W, only depends on the geometrical layout of the resistor. So if this was a thin film resistor, it could be any type of thin film, it could be a metal or a semiconducting thin film or whatever. In this particular case, say you can say that it's roughly twice as long as it's wide. So you can say that in this particular case, L over W is 2, okay? And it doesn't matter to the resistance whether I make the length, say, double the length and I double the width, the L over W terms will still be the same. And the resistance will be given by this sheet resistance times the geometrical layout. So that's a different way of writing the same expression, but it's kind of interesting because it allows you to break down the value of the resistance as a process-dependent term. Process-dependent meaning things like the resistivity of the film and the thickness of the film times the geometrical layout of the resistor, how long it is divided by how wide the film is, okay? Now, if I measured the resistance and I knew what the geometry is, clearly I can then determine rho over the T. And then if I had an independent measurement of the thickness, and there's other ways of doing that I will get into, you're still left with a problem because I get the value of the resistivity, rho, 1 over sigma, which is the product of the mobility times the carrier concentration, mu P times P. Now, ideally, you like to know both. And for that, you have to use the so-called Hall effect, which is shown on the left-hand side. This is an effect that was discovered by a physicist named Hall, Edwin Hall, in the 19th century, end of the 19th century. And it's still very, very powerful. We use this Hall effect measurement all the time. How does it work? Well, you still measure the resistance by applying a voltage along the X direction, but then you also measure the resistance in the presence or absence of a magnetic field B in the Z direction. All right. Now, if I have a magnetic field, you may remember from your physics 303L class, the particles see a so-called Lorentz force, F, given by the charge of the particle. In the case of electrons, it will be minus a negative quantity. For holes, it will be a positive quantity, Q, times E, the electric field, which is given by Vx, the applied voltage divided by the length of the resistor, plus V, the velocity. This small v is not the voltage, V cross product with B. Now let's see how that turns out, okay? In this case, I have a magnetic field only along the Z direction. Therefore, I only have BZ component, okay? And if I have a drift velocity along the X direction, I end up getting Vx cross BZ, and the cross product will be obviously in the Y direction. So there's a force, a deflection force of particles, which will deflect the holes in this direction, and therefore I build up a net positive charge, okay? And if the holes are deflected in this direction, there'll be an excess of holes, and there'll be a deficit of holes, therefore this develops a negative charge over here. Now, if there was a circuit completed along the Y direction, what that would cause is, it would cause a current to flow because of this V cross B term. But of course, I have an open circuit over there. So as a result, all that happens is there's a charge buildup of excess holes on the left-hand side and a deficit of holes, which gives you a net negative charge. And that then develops this so-called Hall field, which just cancels this Vx times Bz deflection force, okay? So that Hall field, Ey, just simple algebra, okay, in terms of the cross-sectional, in terms of the current, which is given by the cross-sectional area width times thickness, times the current density Jx in the X direction. Jx current density has units of amps per centimeter square, okay? Can be written as the cross-sectional area W times T, and the current density due to drift current we saw in the last class is given by the drift velocity V sub x, which for low electric fields is given by mobility, in this case the whole mobility, times E, where E is given by the voltage applied Vx. So this is the voltage. Don't confuse this with the small Vx, which is velocity, okay? Maybe I should write it as a capital V. So the electric field is Vx divided by the length, okay? So I know what the electric field is, and we saw that at low electric fields, Ohm's law is valid. Under those conditions, the drift velocity is proportional to the electric field, and the proportionality constant is what we call mobility, okay? And then times Q times P naught. P naught is the number of holes per unit volume. That is the expression for the current density, okay? Once I write that down, very straightforward algebra, you can write down an expression for the VEY equals this, which depends only on the whole current density, and everything else I'm able to measure because I can use an ammeter to measure the IX divided by the cross-sectional area gives me JX. Presumably, I know what the magnetic field that I've applied. Q, of course, is a hole or the electron charge, okay? And therefore, from the measurement of the Hall field, I can extract what the whole carrier concentration is. From the measurement of the resistance, I was able to get the product of the mobility times the whole concentration. Therefore, using the two measurements, I can independently get both the carrier concentration and the mobility of the carriers, okay? And that's what I'm showing over here. Now, the Hall field, to measure that, all that I need to do is I apply a voltmeter in the Y direction, and I measure the Hall voltage divided by the width of the resistor gives you the Hall field EY, okay? Once again, as I said, this measurement of Hall effect and the resistance is something, if you do research in the field, you'll be doing constantly because you're always interested in, if you make a device, what is my whole carrier concentration and what is my carrier mobility? And these two measurements give you a simple way of measuring those, all right? To wrap up chapter 3, I just wanted to summarize this concept of effective mass. So remember, we started talking about effective mass in terms of the band curvature. So we said that if you had a EK relationship that was sharply curved, since the effective mass depends inversely on the curvature, you'll have a light effective mass. On the other hand, if it's more gently curved, it has a higher effective mass. That is the starting point of defining effective masses based on the EK relationship of the band structure. Now, in general, we mentioned, although we are not going to test you on that in this class, in general, these EK curves have different shapes or curvatures along the X, Y, Z direction. So in general, this effective mass is not going to be a scalar number. It's going to have different values in different directions, and that makes it a so-called tensor quantity, all right? Now, because of that, then when you looked at the density of states, GC, where the GC, the density of states, is the number of GC as a function of energy, dE is the number of available states between an energy E and E plus dE. Okay, so that's how you count available states. Of course, to get the actual number of carriers, you have to then multiply by F of E in the case of electrons, or 1 minus F of E in the case of holes, and then integrate from the bottom to the top of the conduction band. All right. So the point is, we mentioned a few lectures back that when you look at the density of states, you see that you have an effective mass over there, okay, raised to the power 3/2. So then if I have different values of effective masses, M1, M2, M3 along the X, Y, Z directions, then which of these effective masses should I choose in this expression for the density of states? And the answer is, you should take the geometric mean, because you look at the form in which the mass appears in this expression, and then you see that, okay, if I have M1, M2, M3 raised to the power 1/3 for the effective mass in the density of states, kind of you have, dimensional equivalence, okay? On the other hand, last class, when we started talking about carrier mobility, there we see that the effective mass appears in the denominator. So how do you average the effective mass? Well, looking at how the mass appears in the denominator, a rational way of doing that would be 1 over M star for the conductivity would be 1/3 of 1 over M1 plus 1 over M2 plus 1 over M3, okay? So the point is, you don't just choose these definitions of averages arbitrarily. You see how the mass term appears in the relevant expressions for transport or counting states. And depending on that, you use either the geometric mean or the harmonic mean in terms of the band curvature effective masses. Okay. So that concludes our discussion of chapter 3, which is a very important chapter in terms of these concepts of energy band diagrams and concepts of Fermi Dirac distribution function, density of states, and using that, how to calculate numbers of electrons and holes and things like that. Okay, so this is what he'll be responsible for in the midterm coming up on Wednesday. And of course, I've also thrown in one question on quantum mechanics and one question on crystal structure. Okay, I'll email all of you with a few more instructions on the exam. So it'll be held online, of course, and you can scan your solutions and upload them the same way you upload your homework. I mentioned that you can print out the exams that I'll post online about half an hour before the exam start. If you don't have a printer, no worries. I mean, you don't need to print it out. You can just write out the solution on sheets of paper and scan them and upload them. All right, since
How many
yeah.
questions are going to be on this exam?
Four.
Okay.
Yeah.
So one quantum mechanics, one crystal structure, and then
2 on
two
chapter 3.
just on various topics.
Yeah. So one on band structure and band diagrams, and one on transport. Okay. All right. Okay. So chapter 4 deals with another very important topic, which I call excess carriers, which is a concept related to non-equilibrium. So I want to take a few minutes to clarify some basic concepts that people sometimes get confused about. Okay, and the concepts that I want to talk about are equilibrium systems. This is general. I mean, it's not just for semiconductors, versus non-equilibrium. For the non-equilibrium case, you have two subsets. You have steady state and non-steady state or transient. Okay, so what does that mean? Well, when I talk about a system in equilibrium, such as a semiconductor device, basically what I'm saying is that semiconductor device, such as this transistor or my microprocessor chip, is just sitting on the table, lazily, doing nothing. All right. I haven't applied any voltages to the device. I'm not shining laser light on the semiconductor as we discussed in chapter 4 right now. It's just sitting there. Okay. And that's what I mean by equilibrium. So things like the carrier concentrations obviously are not going to change with respect to time. There's no currents flowing, obviously, because I haven't applied any voltages to it, et cetera, et cetera. Okay. However, you have to realize that equilibrium itself can have two forms. You can have what is called static equilibrium or dynamic equilibrium. What does that mean? Well, in the case of static equilibrium, it means that basically things are not changing at all, okay? Everything is static, okay? Now, in practice, at least in quantum mechanics, you can never have static equilibrium. You really have what's called dynamic equilibrium. What does that mean? Well, even if I look at a lump of metal sitting on the table, okay, you might think that it's totally stationary, but obviously you may remember from the physics classes, the atoms in the metal, at least at finite temperatures, are not going to be perfectly static. They're going to jiggle about the equilibrium position, right? That's an example. If you look at the atomistic picture, it's more like a dynamic equilibrium, right? Although if you think of the atom of the metal bar as a macroscopic object sitting on the table, you could think of it as a case of static equilibrium. Well, in the case of semiconductors, it's definitely dynamic equilibrium when it comes to carrier concentrations. Why? Because we saw that in a semiconductor, you can excite electrons from the valence band to the conduction band and create a few conduction electrons, leaving behind positive holes, even in the absence of doping. But then after a few nanoseconds, these electrons and holes would recombine and give off photons to the ambient, okay? After a few nanoseconds, you could absorb a photon from the ambient and re-excite electron-hole pair, okay? And that's in fact what happens even if I don't apply any voltages or shine extra laser light on it, okay? And the reason being, these photons that I'm talking about being absorbed and re-emitted are constantly surrounding us, and that's the so-called black body radiation that we talked about in chapter 2. And that's something that's constantly surrounding us, whether you like it or not, okay? Because, you know, the walls of the room that you're in are at room temperature, 300 Kelvin, and they're constantly emitting infrared radiation, and a few of those photons can be absorbed in the piece of semiconductor, creating electron-hole pairs. But then after a few picoseconds or nanoseconds, those electron-hole pairs recombine, give off these infrared photons to the ambient. So this is constant exchange of energy between the semiconductor and the ambient, okay? And that's in fact what creates this intrinsic carrier concentration Ni, which in room temperature at in silicon we saw is about 10 to the 10 electron hole pairs per second, per unit volume, okay? Now, of course, if I had doping, the picture gets modified because then the donors can create extra majority carrier electrons at the expense of fewer minority carrier holes, and so on and so forth. It's still equilibrium, but it's dynamic equilibrium. It's not a static equilibrium, okay? What does non-equilibrium mean then? Well, non-equilibrium means I can take a semiconductor bar, and as I just discussed in the context of the Hall effect and sheet resistance, I can apply a voltage and I flow a current through that, okay? Now, if the voltage that I apply is a DC voltage, it's going to be an unchanging current. So that's a case of steady state non-equilibrium. The most general case is the voltage that I apply may not be a DC voltage, it could be an AC voltage. So the current itself is varying as a function of time. That's an example of transient equilibrium. Now, when I apply voltages to a device or I shine extra light from a laser, for example, not this black body radiation that is constantly going to surround us, I can't do anything about it. I can turn it off, but I do have the choice of, shining extra light on it and creating excess electron hole pairs. That's also a case of non-equilibrium. Now, if the light that I'm shining was unchanging, that would be a steady state non-equilibrium. But if the light that I'm shining was pulsed, okay, so if I had pulses of light on and off, that could be an example of transient non-equilibrium. So I wanted to keep this concept of equilibrium versus non-equilibrium straight at the back of your mind. Okay. All right. So what I'll start off in chapter 4 is first look at the effects of light, extra light shining on it, hopefully with a photon energy h nu greater than the band gap so that they can absorb those photons and create extra electron hole pairs. We saw in chapter 1, if this photon energy h nu is less than the band gap, it would not be absorbed because then electron in the valence band would try to go up and come to an energy corresponding to the h nu, but there's no states available over there. These are called virtual states. And after a few nanoseconds, it would fall back and the photon would simply be transmitted. It would not be absorbed. All right. So people do these optical studies of photon absorption as a function of the wavelength, which is, I'm showing in a cartoon view over here. Okay. So the type of experiment that you do is you take a thin slab of whatever material I'm interested in, could be a semiconductor, could be a piece of glass or whatever. And on that, I shine a source of light, which is at a particular wavelength, lambda, or a particular frequency, where of course lambda times frequency in the case of electromagnetic radiation is a constant, the speed of light. Okay. And this is a thought experiment. So I can, dial the source of this light. It's called a monochromator. So, I'm choosing specific wavelengths. And then on the other side, I can have some sort of a photon detector. We'll talk about photodetectors in great detail at the end of the course. But basically, in a photodetector, what you have is, if I absorb photons and I create these electron hole pairs, presumably you could hook it up to an ammeter, okay? And these photo-generated carriers might drive a current, and it can measure that photodetected current, okay? That's basically how photodetector works. Now, the details of this I'll discuss towards the end of the course in chapter 8. All right, so you have some way of detecting how much photons are flowing past this thin slab of semiconductor. All right, that's called my transmitted flux, and the incident flux has unit is I naught. Now, what are the units of these photon flux? So I naught or IT has units of number of photons per unit area per second. So it's basically proportional to the intensity of the light that I'm shining. Okay.
What's I
yes,
naught again?
Sorry?
What's the name of I naught again? Like
it's the photon intensity, the light intensity. Photon intensity or photon flux. Okay. So you could convert that intensity in terms of number of photons per unit area per second into units of watts per unit area per second, simply by multiplying the number by the energy carried by a photon, which of course is given by h nu. H nu has units of energy. So that if you multiply by that, you'll convert that to watts per unit area per second of energy flowing on the semiconductor. Okay. So then you can take the ratio of the transmitted flux divided by the incident flux. And from that, you can extract this quantity alpha, which is known as the absorption coefficient. Absorption coefficient, which I can then measure as a function of the wavelength decreasing to the left, or conversely, you can write that in terms of frequency. So as the wavelength, a wavelength increasing to the left, or conversely, if the wavelength increases to the left or decreases to the right, okay? So as wavelength decreases to the light, the frequency nu goes up. So that's what I'm showing over here. So you can write this either as a function of the wavelength or the inverse of the wavelength, which is the frequency, all right? So what it tells you, this measurement tells you is when the photon energy, h nu, is greater than a certain threshold, which is the band gap, I can absorb those photons and the absorption coefficient shoots up. But if the photon energy is less than the band gap, it hardly absorbs at all. And the absorption coefficient is small. Most of the light just gets transmitted through that, okay? Now, one can solve for this light transmission as a function of the thickness by writing down a differential equation of this form, okay? Let's see how we can do that, okay? So the way you do that is, let's look at the magnified view of this slab, okay, of thickness L, but then look at the distance from X to X plus dx. Okay. So I'm claiming that as the light transmits through, it'll die down because it gets absorbed more and more and more. Okay. So at the surface, the light flux is I naught, but then at some distance X, at some depth X, the light intensity will be Ix. It will have dropped some. Okay. And then you can say that between X and X plus dx, the decrease of the light intensity because of absorption should be proportional to the light intensity at X. And the proportionality constant is what I call alpha. Okay. And because it's a decrease of the light intensity because of absorption, you get this minus sign over here. Okay. So you say that the decrease of the light intensity with distance minus bi dx is proportional to the light intensity at distance x, and the proportionality constant is alpha. Now, this is a very simple first order differential equation, so you can solve that. And the solution, of course, is going to be an exponential function, e to the power minus alpha times x. Okay. Then you put in the boundary condition at x equal to 0. I've told you that the light intensity incident on the sample is I naught. Therefore, you can write down I of x equal to e to the power I naught e to the power minus alpha times x. So how much light is transmitted at this end? IT. Well, x equals L. So for the light that comes out, IT would be I naught e to the power minus alpha times L. So if you knew what the thickness of the sample was, and you measure the light coming out by using the photodetector, and you knew, of course, how much light I'm shining in, from the ratio, you can calculate this absorption coefficient, and you can measure that as a function of the wavelength or the frequency of light. Okay, so that's how these optical measurements are done. All right. Now, if you did these measurements for different semiconductors, I'm showing the band gaps of these different semiconductors, and I'm superimposing them on the electromagnetic spectrum. Of course, the electromagnetic spectrum is huge. It extends from very, very high energy, very short wavelength photons, very, very energetic photons, very, very high frequency photons, which are known as gamma rays. Then you have X-rays, and then ultimately you have ultraviolet, and then you have the visible part of the spectrum over here. Okay, so that's a visible part of the spectrum, which of course we're most interested in. But then it doesn't stop there, of course. Beyond red, you have longer wavelengths or lower frequencies or photon energies, which is known as infrared. Then you have microwave, millimeter waves, all the way up to radio waves. Okay, so it's a huge range of electromagnetic wavelengths or frequencies. Okay. Now, the visible part in the case of optoelectronic devices is particularly interesting to us because if I'm emitting light, electromagnetic radiation, it's nice to be able to see it, and so on and so forth. And what I'm showing is, if I look at a semiconductor such as gallium phosphide, one sees that it is a band gap of around 2.2 or so electron volts. Now, for the visible part of the spectrum, if I convert the corresponding wavelengths into photon energies, I find that the blue part of the spectrum corresponds to a photon energy of about 3 electron volts, while red corresponds to about 1.8 electron volts or so. Okay. So what's going to happen if I shine white light in a thin slab of gallium phosphide? Which photons do you think would be absorbed and which should be transmitted? Would the blue photons be absorbed or be transmitted by gallium phosphide? Anybody?
I'm a bit confused on how you would know whether they're absorbed or transmitted. Is it just whether the band is higher or lower, or?
Yes, that's the main parameter. Yeah, if the photon energy is greater than the band gap, it will be absorbed, right, by exciting electron from the valence to the conduction band. If H nu is less than the band gap, it gets transmitted.
And transmitted? Isn't GAS at like 1.5? Oh, wait, no.
Sorry?
Are you asking for GAS?
No, I'm asking for gallium phosphide.
Oh, then it'd still just be transmitted since it's, I think, less than the area of blue.
So blue would be transmitted? No.
I think so, yeah. Isn't
No.
blue farther along the line than that?
Yeah, but it's got higher energy, right? This is a product.
Oh, it's in reverse. That's right.
Right, reverse. Okay, so blue and green would be absorbed, while red and yellow would be transmitted. So if I hold up a thin piece of gallium phosphide semiconductor up against white light, the red and the yellow would pass through that. So that's why gallium phosphide semiconductors look reddish or yellowish, okay? On the other hand, if I hold up a piece of gallium arsenide up against white light, what color do you think the gallium arsenide would have? Would the red through blue be absorbed or transmitted?
All absorbed.
All absorbed.
Observed, so it just looks
So,
black.
so it would look, yeah, opaque, right? Similarly, silicon, of course, silicon is a little bit complicated because it's indirect band gap, but so the efficiency of absorption is weakened, but in spite of that, all these visible part of the spectra would be absorbed, okay? On the other hand, if I take something like silicon carbide, it's a high band gap semiconductor, and I hold it up to white light, what would it look like?
White light.
Transparent, yeah. If I look at glass, that's not shown on this chart, that has a huge band gap. It's an insulator of 9 eV, okay? So if I shine light through glass, would any of those visible parts of the wavelengths be absorbed?
No.
No,
It's
that's why
way too
glass
high
is,
up.
that's why glass is transparent. On the other hand, metals don't have a band gap at all. So most metals are, I mean, all metals are opaque, okay? Now the second order effects, so in glass, you could put in impurities, even though it's got a large band gap, you could put in certain impurities, and then you could have absorption in a two-step process via the impurities, and that's why you can get colored glass, okay? But we won't worry about those details over here. All right, so that was sort of the broad picture. Now you can do a more detailed analysis of this optical absorption as a function of photon energy proportional to the photon frequency increasing to the right or wavelength increasing to the left, okay? And you find that contrary to this very simple characteristic that I showed in this cartoon view, the actual absorption characteristics have a lot more structure. So basically, if I have photon energies greater than the band gap as shown over here, okay, so now H nu is greater than the band gap, you have a strong absorption, okay? But then if you go to even higher energies, notice that the absorption coefficient starts dropping off because bands have a finite width. And therefore, for very high energies, the density of states drops off by the time you go to the next band gap, okay? Now, the structure below the band gap is more interesting. So you find that, contrary to what I showed in the previous slide, there is absorption even below the band gap. And those are due to some of these defects that I mentioned. So for example, in a semiconductor, we of course have donors and acceptor type impurities, okay? And those could participate in this absorption process. So for example, as shown over here, you can have excitation from the valence band to the donor level. Instead of valence band to the conduction band, valence to the donor level. Now, is that a lower or greater energy than the band gap? Band gap is from EC to EV. So if I had an excitation from valence to the donor level, that photon energy would be smaller, right? Smaller by whatever the donor binding energy is. And that's what I'm seeing over here. So from the shift, you can estimate what the donor binding energies are, okay? Similarly, you could have excitation from the acceptor level to the valence, sorry, that's EC and that's EV. My apologies. You can have excitation from the acceptors to the conduction band. Notice that it's at a slightly different energy, okay? So basically from these, you can get the donor or the acceptor energies, okay? Now you can also have excitation from the donor to the valence band, and that's much smaller energy, of course, or valence band to the acceptor, okay? Could also have absorption due to what are called optical phonons. In the last class, remember we said that these phonons are lattice vibrational modes, where the quanta of those lattice vibrations are called phonons. And we saw that you could have different flavors of these vibrational modes where these neighboring atoms could vibrate in phase. Those are called the acoustic phonons, or they could vibrate in opposite phase. Those are called optical phonons. And when they vibrate in opposite to each other, that is more energetic. So you have optical phonon absorption. So the point is, you can get a lot of insight about the physics of what's happening in the semiconductor from these optical studies, okay? Optical absorption studies. So these absorption due to impurities are shown in more detail over here. So you can have direct absorption processes from valence to the conduction band, or as I said, you could involve the impurities. For example, these carriers in the conduction band, which might be initially at a very high energy. These are hot electrons, lose energy by emitting a whole bunch of phonons, then relax to this impurity level. Subsequently, it might be excited from the impurity to the conduction band and then fall down, or it could come from here to the valence band. So you have all these complicated processes that can go on. So from this photon energy, for example, you could measure what the trap impurity level is, okay? The ET is the so-called trap level. And these are energy levels that are introduced in the band gap by different kinds of impurity atoms or defects, okay? Now, one example, of course, that we've already talked about are these donor or acceptor type impurities, which are introduced intentionally to create excess electrons or holes in the semiconductor, okay? But in addition to this donor and acceptor type of impurities that I engineer in, you could have other kinds of unintentional impurities or structural defects, which could introduce energy levels in the band gap. Those I call traps. Now, in terms of the generation recombination processes, some of these traps can be close to the band edges, either the conduction band or the valence band, in which case these are known as shallow impurities. But if they're close to the middle of the gap, those are called deep impurities or deep traps. And sometimes they're also known as generation recombination centers. So traps near the middle of the gap are given a special name. They're called deep level impurities or generation recombination centers. Why? Well, to understand that, you can look at this diagram where now I'm showing trap level impurities, which are deep traps, or generation recombination centers, okay? And these can be very, very effective in recombining electron hole pairs or generating electron hole pairs, more so than shallow traps as shown over here. Why is that? Well, let's look at the shallow trap and see how it might help in a generation process of electron hole pairs compared to direct band-to-band generation. So for direct band-to-band generation, I'd have to take a photon with an energy greater than or equal to the band gap so that I go directly from the valence to the conduction band. By contrast, if I had a trap level ET, I can make do with lower energy photons corresponding to the energy separation between the valence band and the trap level. So I first excite it to the trap level, and then from the trap level, using another low energy photon, go to the conduction band. So obviously, these two-step processes, each step requires a lower energy photon, and generally have more of those than the higher energy photons in the ambient. And therefore, these two-step processes are going to be easier, okay? The analogy that I use is, if you ask me to step onto a table from the floor, given my arthritis, I have a hard time, okay? I won't be able to do that. But you gave me a small stool, I could easily step on the stool and then from the stool onto the top of the table, okay? So these are like stools which help two-step processes. Conversely, if I have a trap level like this, I can take electron in the conduction band and it falls into this trap level and then subsequent emits a photon, and then subsequent from the trap level into the valence band emits another photon. The nice thing is, if I have such trap levels, that can also help with generation recombination processes in indirect bandgap semiconductors such as silicon. You may recall that in indirect semiconductor, if I plot E as a function of K, the minimum in the conduction band is at a different value of K as maximum of the valence band. And that generally involves a phonon to carry out the momentum change, and then a photon. So it involves a photon for the energy part and a phonon to carry the momentum. Where it turns out that if I had trap levels, these trap levels can also help take care of this momentum conservation. So this trap assisted generation recombination processes are very useful in indirect band gap semiconductors, especially. Okay. All right. So going back to this analogy of the trap level being like this intermediate stool between the floor and the table, let me ask you, which trap level would be more effective in this generation recombination processes? If I had a trap near the middle of the gap, or if I had a trap level which is close to, say, the conduction band? Case 1 or case 2? Which type of trap would be more effective in creating easier pathways to generation of electron hole pairs?
So do all electrons go through the trap level, or is it just some of them?
Some of them. So there's multiple paths, processes that can happen in parallel. So if I had photon energies greater than or equal to the band gap, it could go straight from the valence to the conduction band. Okay, you don't need to involve the traps. But what I'm saying is, if I had trap levels in the middle of the gap, you could also absorb photons with an energy lower than the band gap. All right. So the question for you guys is, given
Wouldn't EF allow more to go through because it could have ones that are lower energy? I think the thing I'm confused about, I don't necessarily understand why it still has to travel the full, like, I guess, energy distance, quote unquote.
right.
So why is it taking less energy to be able to get in between them?
No, it's not taking less energy. What I'm saying is, if you look at the black body spectrum, okay, that I showed in chapter, well, it wasn't in the book, but I showed in the notes. Remember, we said that if you look at the black body spectrum, this is the intensity as a function of photon frequency. You have fewer and fewer high energy photons. You have more and more lower energy photons. Okay.
Yeah.
Remember that?
Yeah.
So in the environment, generally speaking, you'll have a lot more of these lower energy photons, and those could then be absorbed if I had traps in the middle of the gap. Okay.
Like, would you need more than one trap in some examples for them to keep jumping between layers?
It could, but what I'm saying is, if I had a trap level, you certainly need at least 2 photons, right? The first photon to go from the valence to the trap level, and the second photon to go from the trap level to the conduction band. But the 2 photons could have different energies depending on whether the trap is exactly at the middle of the gap or offset in the upper half or the lower half. The total energy required is still the same. Okay. So the 2 photons collectively must have an energy equal to or greater than the band gap. So I'm not saying that you require less energy. All that I'm saying is, since I have, generally speaking, more lower energy photons in the environment and fewer of highly energetic photons, the presence of traps makes it easier to absorb some of these plentiful lower energy photons. Plus, these traps can take care of this momentum conservation that you need to satisfy. You always have to satisfy energy and momentum conservation. Okay, so these trapped atoms can vibrate and carry off some of this excess momentum or provide excess momentum and so on and so forth.
Okay.
Okay. So this mid-gap trap, so there's still a question pending for you guys. So if I had a trap which was near the middle of the gap, which I call trap type 1, versus shallow traps, which I call trap type 2, which type of trap do you think is more effective in generation recombination type processes? 1 or 2?
I mean, the first, like, 2, since wouldn't it need, I mean, you'd need one higher energy photon, but you'd also need one very low energy photon just to get there.
Right. So it turns out 1 is more favorable because, once again, you have plentiful low energy photons, right? So you're sort of on the right track, but you got off track, right?
I think the thing I just don't get is, like, you would need a lower energy photon to go to EF.
It's
But
not
then
EF, it's ET. And then you'd need another lower energy photons to go to EC.
Yes, in the mid one, you'd need like 2 roughly of the same energy level.
Right.
But if it's closer to the band gap, you'd need one that's lower and one that's higher.
Right.
But how do you necessarily know that that's more effective? Like,
Okay, so
How
go
do
back
you
to
know
this.
you have more mid-range photons than one low and one high?
Right, very good question. So go back to this analogy that I mentioned. Okay, so I have to step onto a table, okay, from the floor. If you gave me a stool, which was, a very shallow stool, right, close to the floor, versus another stool, which was sort of halfway in between, versus a third stool, which is just a little bit below the tabletop, which stool do you think is going to be most helpful for me, given my arthritis?
Probably
A
the
very,
center stool.
the one in the middle, right?
Yeah.
Right. So that's sort of the analogy. Okay. So the ones in the middle of, near the middle of the gap are the most effective in creating generation recombination sites. Okay. They're called deep traps.
Okay. So all that
Now,
really matters is like the end result of getting to that other band gap.
right. Exactly. Okay. Now, when you have these trap levels, you have 4 different types of processes that can go on. So you can have recombination of electrons, which I call RN. Inverse process is generation of electrons, and similarly generation and recombination of holes, and so on and so forth. Okay. Now, someone, maybe you or someone else, raised another important point, and that is, what if you have multiple types of traps? Okay, so not all the traps may be at this energy. We have some over here at this energy, some more over here. Let me call that ER1, ER2, and then ER. Okay, so then you could also have more complicated processes from ER to ER1, ER1 to conduction band. So things can get horrendously complicated, and you can write down these differential equations involving, multiple trap levels. So that kind of physics is known as Shah noise Shockley type processes, while processes involving a single type of energy level trap are called Shockley-Reed-Hall type processes. Okay. Now, clearly, Shah noise Shockley is going to be horrendously complicated. So in our class, all that we'll deal with are these Shockley-Reed-Hall processes, SRH type processes. Okay, single energy level traps, and even there, all that I'll be responsible for is this qualitative description that we just went through. Okay. Now, if you took a graduate course, you'd write down differential equations for all these processes, and then you could solve, for the carrier constellations as a function of time and so on and so forth. But in our class, we'll do just one simple example in the next slide, but by and large, it'll be mostly a qualitative picture. Okay. All right. So what I'm doing next is essentially a worked out example, but a worked out example that introduces some key concepts. Okay. And example that I'm working out is I have a semiconductor, which is doped p-type at 1 × 10⁻⁵. And on that, I'm shining laser light. So this is non-equilibrium. Laser light H nu greater than the band gap at a flux where I create excess electron hole pairs. So I'm exciting electrons from the valence to the conduction band, and I'm creating excess holes, delta P equal to delta N. But in this case, I have chosen a p-type semiconductor. So I had a starting hole concentration of P0, which in this case is 1 × 10⁻⁵. But then delta P is 10⁻⁴, or 0.1 × 10⁻⁵. So the resulting hole concentration, majority carrier hole concentration, is 10⁻⁵ plus 10⁻⁴ due to the electron hole pair creation, or 1.1 × 10⁻⁵. Okay. On the other hand, if I look at the minority carrier concentration, delta N, because of the number of photons per second that I'm shining in, I'm creating 10⁻⁴ minority carrier hole concentration. So delta N equals delta P equals 10⁻⁴ per centimeter cubed, while P0, the starting hole concentration due to doping, is assumed to be 10⁻⁵. Okay. So I shine light on it, and I assume that the film is thin enough that it's more or less uniformly being absorbed. Okay. In practice, of course, we saw that if it was a thick sample, the light intensity would die down exponentially with distance, but I'm assuming a thin enough bar that it's almost constant. Okay. But then what I do is at time t equal to 0, I turn off the light source. Okay. So I have the light that I turn off at t equal to 0. And then I notice, I try to calculate the carrier concentration of minority carrier electrons and the majority carrier holes as a function of time in nanoseconds. Okay, so that's what I'll try to solve. Okay, by writing down an appropriate differential equation. Now, assuming this was silicon, does anyone remember what Ni is, the intrinsic carrier concentration?
10 to the 10.
Very good. At room temperature. At higher temperatures, it's going to be higher. Okay. So we saw in chapter 3 that N times P is equal to Ni square. So if my starting hole concentration was 10 to the 15, what is my starting minority carrier electron concentration in this p-type semiconductor? Ni is 10 to the 10, so Ni squared is 10 to the 20 divided by 10 to the 15. So N in the p-type semiconductor is 10 to the 5, right? So then I see that once I shine light on it, I add delta N to this. So 10 to the 5 plus 10 to the 14, what is that approximately equal to?
10 to the 14.
10 to the 14, okay? On the other hand, for the majority carriers, the starting concentration was 10 to the 15, and I add 10 to the 14, so I get 1.1 times 10 to the 15, okay? So what is the message over here? The message is, although I'm creating exactly the same number of excess electrons and holes, the change of the majority carrier concentration on a fractional basis is pretty small. It's only a 10% increase, while the change of the minority carrier concentration on a fractional basis is humongous, right? It's going from 10 to the 5 to 10 to the 5 plus 10 to the 14 or 10 to the 14. So 9 orders of magnitude increase of the minority carrier concentration, but only a 10% increase of the majority carrier concentration. So that's a statement that's always going to be true, okay? On a fractional basis, the change of the minority carrier concentration is always going to be larger than the change of the majority carrier concentration, although the absolute changes are going to be the same if I have a direct generation of electron hole pairs, right? Now, I've turned off the light and I want to see the rate at which these electron and holes recombine and of course give off photons. So question, is this a equilibrium or a non-equilibrium problem?
We're using N naught and P naught, right? So isn't it equilibrium problem?
Well, N naught and P naught will be equilibrium, but now I'm shining extra light and creating excess carriers, right? So that makes it
Out of equilibrium.
non-equilibrium, right? Is it steady state or transient? Well, if things are changing as a function of time, there'll be a transient non-equilibrium problem, right? So what I have to do is I have to somehow write down a differential equation describing this transient process, and that's what's shown down below, okay? So where you write it down is I look for the number of minority carriers as a function of time, dn dt. So I'm writing n, the minority carrier electron concentration, as a time-dependent part, okay? And I can write that as the difference of a generation rate minus the recombination rate, okay? Now, if I have few electrons and holes, no, sorry, if I have many electrons and holes that I've created, delta n and P naught plus delta P, versus a scenario where I have only a few electrons that I've created, in which case do you think this recombination process would be more rapid? The case where I have a lot of electron and holes, or the case where I have few electrons? But the number of holes, of course, is governed basically by the doping P naught, right? Case 1 or case 2? In which case would the recombination occur more rapidly?
I mean, the more electrons and holes you have, the more transfer there is, right?
Right. So there'll be more recombination, right?
Yeah.
So the recombination rate can be written as the product of the number of electrons times the number of holes. Both of these, notice, are time-dependent term. And the proportionality constant is what I call alpha R, which is the recombination rate constant. Okay. So the recombination rate, you can sort of infer based on physical intuition, should be proportional to the product of the number of electrons and holes. If you have more electrons or more holes, they can recombine faster. And the proportionality constant is what is known as the recombination rate constant, alpha R. Don't confuse this with the absorption coefficient that I showed previously. Okay, although ultimately they are related, but it's a different proportionality constant. Now there's also the inverse generation process, whether you like it or not. Okay, why is that? Well, remember we said that we are surrounded by the walls of my room, which is at room temperature, and that's going to constantly emit black body photons, right? That excite carriers, electron hole pairs, but then after a few nanoseconds, those electron hole pairs recombine, give off black body radiation. So this is black body photons, not the laser light that I'm shining on top of it. Okay. Now, assuming there's no laser light shining on it, this black body absorption and recombination process is what establishes this Ni. Remember that? This intrinsic carrier constellation is because of this dynamic equilibrium that you have with the surrounding environment. Okay, and that's what establishes N sub I, the intrinsic carrier constellation. Okay, and that's going to happen regardless of whether I'm shining a laser or not. All right. Now, if I didn't shine the laser, this semiconductor was just sitting there and had a carrier constellation Ni. What must happen to the generation rate versus the recombination rate due to purely black body? They must equal each other, right? That's what's establishing the dynamic equilibrium, right? I'm absorbing black body photons. That's my generation rate, creating electron hole pairs. And then those electron hole pairs subsequently can recombine, emit black body photons. So that's a recombination rate. And these two rates, generation or recombination with black body photons, must obviously equal each other. All right. So what is going to be the recombination?
Is this just the rate at which the electrons are filling holes and new holes are opening up?
Exactly. So it's a dynamic process, right? So this semiconductor bar has a valence band and a conduction band, right? The black body photons are being absorbed, creating electrons and holes, but they just don't stay there. Okay, it's an unstable scenario. So subsequently, these electrons fall into the hole state, re-emit photons. Okay, you absorb more photons, you create more electron hole pairs, they recombine, emit photons, and it's a constant exchange of energy with the surrounding environment, and that is what what establishes the intrinsic carrier constellation N sub I. Okay. Now, going back to my expression for the recombination rate, which is alpha R times number of electrons times number of holes, what do you think? What do you think will be the recombination rate? It will be alpha R times the number of electrons times number of holes in equilibrium now. And what is that equal to? In equilibrium, N times P equals to Ni squared, right? And therefore, the generation rate must also be equal to that, alpha R times Ni squared. I'm going to repeat this, and I know it's kind of tricky because you're throwing a lot of subtle physical ideas in. So let me go through this and then I'll repeat it again. Okay. So I'm saying that the generation rate due to black body photons must be equal to alpha R times Ni squared. All right. And now I move to the scenario where I'm actually shining laser light for a while, creating excess electrons and holes, and then turning off the light at time t equal to 0. And I want to see the rate at which these electron and hole carrier concentrations decay back to the equilibrium values. Okay. If we waited long enough, the whole concentration would decay to what?
Can you repeat the question?
If I waited for a long time, okay, after I turned off the laser light, what would the whole concentration go down to?
0. Wouldn't there be no transfer once there's no?
No. So remember I said that
electrons.
I started with a p-type semiconductor doped at 10 to the 15, right? So I get 10 to the 15 acceptors, right? 10 to the 15 holes.
Oh, I thought you were asking about the rate of transfer once. Oh, okay.
The rate of net transfer would be 0, okay? Because the generation recombination rate due to black body radiation, the difference of those is 0. The generation rate equals the recombination rate. But now I'm looking at the laser light that was shining, and then at time t equal to 0, I've turned off the light, right? And I want to see how the electron and the whole concentrations are changing as a function of time. Okay, so because I've chosen a p-type semiconductor doped at 10 to the 15, if I waited long enough, the whole concentration would asymptotically approach 10 to the 15. How about the electron concentration, N naught? What would that asymptotically go down to?
And the negative 15? Actually, just go down to 0, right? There's
No.
once you fill up all the holes. I think
No. What is N naught times P naught equal to? Ni squared, right? So if P naught ultimately goes down to whatever the accepted doping concentration is, 10 to the 15, N naught would be 10 to the 5. Okay, and that's not shown on this chart because this only goes down to 10 to the 12. So if you waited long enough, it will keep decaying and ultimately settle down at 10 to the 5 electrons. That's my N naught, while the whole concentration would be P naught, 10 to the 15. And 10 to the 15 times 10 to the 5 gives you 10 to the 20, which is Ni squared. Okay. All right, so let's go back to this differential equation. So I want to see what the decay rate is of the number of electrons, the minority carrier electrons. And I can write that as the generation rate due to the black body photons, which is alpha r times Ni squared, minus the recombination rate, alpha r times N times P, which are time-dependent quantities. I write down N as N naught plus delta N, and P naught, P as P naught plus delta P. Okay. Now, which one is larger, N naught or P naught in this particular case?
P naught.
P naught. Okay.
not larger.
Yes. So when I multiply these out, simple algebra, okay, you'll get these terms. Okay. You'll get N naught plus P naught times delta N, and then you can ignore the minority carrier concentration. And then you get a quadratic term, delta N times delta P, but delta N equals delta P. So I can write that as delta N squared. Okay. And then for low numbers of excess carriers that are created, that's known as low level injection, you can ignore the quadratic term. So we now linearize this equation. All right. So what I end up getting then is dn. Oh, and then the other term that you get is N naught. You get a term N naught times P naught. That's Ni squared. That'll cancel with this Ni squared term over here. Okay. So the net result is you'll get dn dt, which is equal to dn naught plus delta n dt. Now dn naught dt is 0 because that's a constant, right? Your dn dt is the same as d dt of delta n equals minus alpha r p naught times delta n. And this is, of course, a time-dependent term. And what is the solution of this? The solution of this is an exponentially decaying quantity. Delta n of t is equal to the starting value of delta n. In this case, that was 10 to the 14, e to the power minus alpha r p naught times t. Now, alpha r times p naught can be written as 1 over tau, but tau is called the generation recombination lifetime. So you see that delta n decays exponentially with time. Delta n equals the starting value, e to the power minus t over tau. Now here in this particular plot, I'm plotting it on a semi-log scale. So I'm actually plotting log of delta n as a function of time. So if I take the logarithm of this, you get a straight line, okay, with a slope of 1 over tau. Everybody with me? So, of course, you don't have to worry about all of this for the midterms, okay? So, think through this, and then after the midterms, I'll start off at this point and go over it again because it's such an important concept in terms of carrier concentrations. Okay? Now, sometimes you will have a high enough carrier photon flux where the number of electrons and holes that I create are actually quite large. So delta n or delta p can be large, in which case you cannot ignore the delta n squared term. Okay, so that's known as high level injection. High level. So the only difference between the high level case and the low level case is, in the case of low level injection, you can ignore this quadratic term delta n square, but for high level, you actually have to solve this quadratic equation for delta n. All right. So I've given you some homework problems that you'll have to solve after the midterms. So whenever I tell you low level versus high level, in low level, you can ignore the quadratic term. In high level, you have to solve the quadratic. Okay, that's the only difference. All right, so next what I can do is I can solve for this differential equation in steady state. So what does that mean? Well, in steady state, I'm shining the laser light on it. And unlike this particular problem where at time t equal to 0, I've turned off the laser light, I just keep the light shining on it. Okay? And I create a steady state non-equilibrium excess carrier concentration of delta n and delta p. How do you solve that problem? If I have a steady state problem in this differential equation, what is dn dt going to be equal to?
Zero.
0. Very good. So then I said this equal to 0 in steady state, okay? And all that I need to solve for is the right-hand side, set it equal to 0, okay? And then you'll have the two cases. For low-level injection, you can just ignore the quadratic term, okay? And under those conditions, then you'll get delta n will work out to alpha r let's see over here. Okay, so in steady state, by setting dn dt equal to 0, okay, you then can write down the thermal generation rate, which is due to the black body photons, which is alpha r times n naught p naught equals alpha r times ni square, okay? But then by shining extra laser light on it, you get a net generation rate, which is g of black body, gt, plus optical generation rate, which would depend on the photon flux, okay? That will be equal to this alpha r times n times p, because now remember, I'm looking at the steady state case. That can be written as alpha r times n naught plus delta n, p naught plus delta p, where delta n equals delta p, okay? So if you knew what the generation rate due to the photons are, the laser photons are, you can solve for delta n or delta p, the excess carrier concentration. Now there'll be the two cases. In the case of low-level injection, the quadratic term, like I said, can be dropped off, okay? In which case, the delta n times alpha r n naught plus p naught equals optical generation rate. The g of t cancels with the n naught times p naught term, because n naught times p naught equals ni square. All right. So under those conditions, then you end up getting delta n in steady state would be equal to the optical generation rate divided by p naught times alpha r. Okay. I'm pretty sure this is quite confusing. Okay, my apologies. I think the best thing might be just focus on the midterms for now. Okay, don't worry about this. After spring break, you get a chance to solve the problem, and then I'll go over this again so that hopefully it becomes clear. Okay, let me just summarize what I've described so far. So what I'm trying to solve for is the problem of carrier constellations that are created by a laser light shining on a piece of semiconductor that I turn off the laser light at time equal to 0. And I want to study the decay of the minority carrier electrons in this case as a function of time, as well as the decay of the majority carrier holes as a function of time. Holes are the majority carrier because my problem statement states that I start with a p-type semiconductor doped at 10 to the 15. Okay. To solve that, you first write down a differential equation, dn dt, which is the time rate of increase of the whole of the minority carrier electron constellation, which is written as the difference of the generation rate, where the generation rate is due to black body photons that I'm absorbing from the ambient, minus the recombination rate. And the key physical insight is that the recombination rate should be proportional to the number of electrons in the conduction band, n of t, times the number of holes in the valence band. And that makes more sense, right? Because if you have a lot of electrons and holes, there's more opportunities for the electrons to fall into the vacant hole states. If you have very few electrons and very few holes, the rate at which they'll recombine would be lower. Okay, so that's really the key concept. The rest is just algebra. So then we write down n of t as n naught, the minority carrier constellation. In this case, that will be 10 to the 5 plus delta n, but the delta n depends on how much laser photons are being absorbed. Okay, times p, which is p naught plus delta p, where the fractional change of n, we said, is much larger than the fractional change of p. The majority carrier change on a fractional basis is much smaller than the minority carrier change. Now, if you work out this product of n times p, you'll see that the n naught times p naught gives you ni square, which cancels with the generation term, alpha r ni square. Okay. Now, you can also ignore the n naught with respect to p naught because minority carrier constellation is much smaller than the majority carrier constellation. Okay. Now, you'll have a linear term, delta n, plus a quadratic term, delta n square. The term low-level injection means the light intensity is so low that the injected carrier concentration is very, very small, in which case you can ignore the delta n squared term, the quadratic term, which makes the problem very, very simple. It's just a linear equation, okay? And that in steady state, where dn dt is equal to 0, gives you the solutions that are shown on the right-hand side. Okay, so you write down the thermal black body part, which is g of t, which only depends on temperature, plus the optical generation rate, which depends on the laser flux, equals the recombination rate, which is alpha times n times p, n naught plus delta n times p naught plus delta p. You work out the products. The n naught p naught gives you ni squared, which will cancel the g of t term. Okay. The delta n equals delta p, so that gives you a quadratic delta n square and a linear term proportional to delta n. In the low-level injection case, you can ignore the delta n squared term, you just left with the linear term. But in the high-level case, you have to actually solve for this quadratic equation. Okay. Anyway, from this, you can get the excess carrier concentrations, delta n or delta p, which will work out to the optical flux, the optical generation rate, times what's called the generation recombination lifetime, which can be defined as 1 over alpha r times n naught plus p naught. And once again, if it's a p-type semiconductor, this can be approximated as simply 1 over alpha times p naught, because n naught is much smaller than p naught. Okay. The final complication is if I now also have traps, they can play a role, and the main difference now becomes in the direct band-to-band process, the lifetime for electrons must be equal to the lifetime for holes, obviously, because you have electron-hole recombination or generation directly from band-to-band. But if I have traps, then the lifetime for electrons, tau n, in general, can be different from the lifetime for holes. Okay. Now, once I get these carrier constellations that are created optically, those carrier constellations in the transient case can be a function of time. You can then write down an expression for the conductivity in the presence of light that's known as photoconductivity. Conductivity we saw is given by the electron charge times the carrier constellation times the mobilities due to either electrons or holes. So now, basically what I see is the conductivity in the presence of extra light shining on a piece of semiconductor is enhanced because of this optically generated electron holes. Okay, and that is a phenomenon known as photoconductivity, which has many, many uses. So a simple example would be in your garage door opener, where you have a piece of semiconductor at one end and a laser at the other end. So when the laser light shines on that semiconductor bar, it changes its conductivity and it triggers a circuit, and the garage door opens up. But then if you interrupt the thing, sorry, the garage door can close. But then if you interrupt that light, for example, by standing in the path of the laser beam, the number of electrons and holes that are photogenerated in that semiconductor detector on the other end goes down. The conductivity goes down, resistance goes up, and that triggers a simple circuit driving the motor, which causes the garage door opener to open up. Okay. All right. That's all that I have. So after spring break, we'll start off with, we'll continue with the discussion of excess carriers moving in a semiconductor by a phenomena called diffusion, which is a motion of particles, either electrons or holes, not because of electric field, but simply a statistical motion with random Brownian motion from a high concentration region to a low concentration region, which you'll see is given by the concentration gradient, dN dx, times the proportionality constant, which is called the diffusion coefficient, either for electrons or holes. That gives you the current density if you multiply by the charge of the electron or the charge of the hole. Any questions? All of this that we discussed today, except for the Hall effect, is off limits for the midterm. All right.
Really quickly,
Yeah.
just in the future, I know one thing that I'm kind of having trouble with when it comes to the homework and stuff is really being able to individually find like, I guess, definitions of each variable. Like they're described in the book, and I know they're in the lecture slides, but a lot of times they're just in the equations. So is there any way you'd recommend kind of being able to just look up specifically like what is this variable and what is this variable?
Yeah, that's all given at the end of the book. If you look at the appendices, they're all listed at the end.
I looked through some of them, like I looked through some of the appendices, and I know that it mentioned some, but when it came to like some of the subscript stuff, I wasn't able to find everything I was looking for.
Well, unfortunately, there's so many symbols, it's hard to list all of them. And a lot of it depends on the context. So you really have to look at the chapters, unfortunately.
Okay. Thank you.
Sorry. Yeah. All right. Good luck in the midterms. Okay.